Okay, so we're going to figure out when series converge or diverge. In this case, a very special series called a geometric series. All right? Consider the following series. This is called a geometric series. This is section 9.2 now. All right, so geometric series. It's of the form thus, okay? It's going to be the sum, as n goes from 0 to infinity, of a times, a is some constant, r is some constant, to the n is the variable. There's n. What does that mean? Well, if you plug in n equals 0, what do you get? What's r to the 0? 1. So 1 times a is a. Remember, the series means add up all the terms you get. All right, so not only going to write out the sequence terms, I'm going to add them up. Plus, plug in 1, what do you get? Plug in 1 for n. A times r to the 1. Plus, what's the next term? A plus r to the 2, and so forth. Okay. Now, that's an infinite geometric series. They come up a lot, and it's going to be really important to know whether they converge or not, and in fact, what they converge to. It's very hard to know whether something converges or not, first of all, much less what it converges to if it converges, okay? So that's what's nice about geometric series. So that's an infinite series. Let's simplify this a little bit. Let me talk about just a finite series. Let me call S sub n the sum of the first n terms, okay? Let that be a plus ar plus ar squared plus blah, 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 ar to the n. Actually, it's n plus 1 terms, isn't it? S sub n is n plus 1 terms, isn't it? Like, if n is 2, I really have 3 terms. Okay, so don't get confused. Where you stop, if you stop at 10, you really have 11 terms, right? I said the first n terms. No, it's first n plus 1 term. What I want to know is what S is. What does it add up to? Can I get a formula for this? And actually, it's very easy. Look at this. What if I multiply this whole equation by r? This r. No, by the way, let me give you some terminology. A is the first term. Did I really have to tell you that? It's the first term, isn't it? R is the common ratio. R is the common ratio. What does that mean? To get the next term, you multiply by R. To get the next term, you multiply by R. To get the next term, you multiply by R. Isn't that Zeno's paradox? First term was 1/2. Times a half is a quarter. Times a half is an eighth. Times a half is a 16th. That Zeno's paradox thing, that was an example of a geometric series. That converged to 1, right? Did it converge to 100% of the path for the arrow? Right? Okay, so I'm still talking about stuff we were doing yesterday. So what if we take this whole thing and multiply by the common ratio? Look what happens. Multiply everybody by r. A times r is ar. I'm going to line up like terms, okay? Ar times r is ar squared. Ar squared times r is ar cubed. It's in here somewhere. Somewhere along the line, you're going to end up with ar to the n, right? Then ar to the n times r is, well, ar to the n plus 1. Okay. I got 2 equations. Can I subtract them? What if I subtract the bottom from the top? Look what you get. This whole thing from the top. What's S sub n minus r times S sub n? Well, that's what it is. But what happens here? AR minus AR? What happens? Poof, 0. AR squared minus AR squared, AR cubed minus AR cubed, AR, right? AR to the n minus AR to the n, all cancel out. What's left after you cancel everything out? A plus this thing, okay, plus AR to the n plus 1. So look, I have an equation for S sub n. I can solve for S sub n. I can figure out what this thing adds up to. I'll go to the next page. I have S sub n minus r S sub n equals, what the heck was it? A plus AR to the n plus 1. All right, notice S sub n is a common factor. Factor it out. A is a common factor. Factor it out. That's r to the n plus 1. So how do you get this alone? That was my original question. What is the finite sum the sum of a finite geometric series? What's S sub n? Get this alone how? Divide by 1 minus r. So S sub n equals a times 1 plus r to the n plus 1 over 1 minus r. Okay, now let's revisit one of the questions we were talking about yesterday. Remember the the Caliph of Baghdad question? He gives you a penny the first day, and 2 pennies the second day, and 4 pennies the third day, and so forth. Right? 8, 16, 32, like that. What does that add up to? Well, if I talk about, let's say, the first 3 paychecks, what are they? Plug in n equals 0, what do you get? 1 plus n equals 1. 2 plus 4 is, I got $7 in the bank, or 7 pennies, right? Okay. Does this formula work? Does it give you that? Let's find out. What's A? A is the first term, 1. What's R? I'm multiplying by 2, I'm multiplying by 2, I'm multiplying by 2, right? So if I apply this rule to this problem, I'm going to say A is 1 times 1 plus 2 to the n plus 1 over 1 minus, who's R? 2. Now what's n plus 1? I stopped at 2. So what's n plus 1? It's 3. In other words, this number up here, again, is the number of terms I'm adding up, 3 terms. Is this, in fact, 7? It is, right? Because 1, no. Oh, I did a boo-boo. Wait, hang on. What? Boo-boo, bad. What happened? That's a minus, right? I subtracted the bottom from the top. Oops, sorry. That should be a minus. I knew something looked weird. So that's a minus. So that's a minus. Dang it. Oh, this is working so nicely. And that's a minus. And that's a minus. All right. So, whoops. Isn't that 1 minus what? 8 is negative 7 times 1 is negative 7 over what? Negative 1. So negative 7 over negative 1 is 7. Right. Okay. What if I go m times? What if I change this? I said, okay, I'm going to go m times, whatever m wants to be. M could be, 31 days. Remember the problem? This comes up with Anastasia's question yesterday. Isn't it 2 to the n plus 1 minus 1? Remember? That's what it is. Look. If I keep on going up to a finite number of terms, but I don't know what it is. Could be some big number, m, whatever it is. What is it going to be? Let's do this rule. It's going to be the first term, 1, times 1 minus the common ratio, 1 minus 2, to the m, where you stop, plus 1. All right, so a and r and m over 1 minus 2. So what do you get? 1 minus 2 is negative 1. If I divide negative 1 into this, I just change everybody's sign, and it's 2 to the m plus 1 minus 1. Isn't that what you were trying to say yesterday? Yeah, it's true. But that's, again, a fluke of, first of all, 1, it's powers of 2. 2, it's geometric. Okay, so. All right, so. Let's see. What can we do with that? What else can we do with that? Okay, so that's a geometric series. What if, now the question is, can I use that to figure out if a infinite geometric series converges or not and what it converges to, right? Okay, that's what I want to get to. But, all right, let me try one other example like this. Let's say a bank account problem. Let's say I deposit $1,000. 0 is like before the first year of interest. So B1 is how much money do I have? after 1 year's interest, okay? I'm going to make this an annuity. Not only am I going to get, let's say, 5% interest every year, I'm going to throw in another $1,000 every January 1st. So the beginning of every year, I'm going to throw in $1,000, plus every year I get 5% of whatever's in there. So how much money do I have at the end of the first year? I put in $1,000 now. A year from now, what am I going to have? Let's say today's January 1st. So a year from January 1st, what am I going to have? I'm going to have 1,000 times 0.05 plus 1,000 that I had, because that's just the interest, rate times principal, right? Plus, then I say I'm going to put another $1,000 in there, right? I'm going to have the 1,000 I started with. I'm going to have the interest on that 1,000, plus I just plunked down another 1,000. Okay, hang on. Let me write this more compactly. Is that the same thing? 1,000 times 0.05 plus 1,000. Factor out 1,000. You get 1 plus 0.05. Okay. I'm making a little room here. All right, what happens after 2 years then? 2 years from today, what do I get? I put in $1,000 today, put in $1,000 a year from today, plus I got some interest. Don't I get interest on this, plus I plunked down another 1,000? Remember, how did I get interest? I just took this, the money I had, and multiplied by 1.05. Well, this is the money I had. So multiply this by 1.05. And plunk down another $1,000. That's not a savings account, that's an annuity, where you put in a certain amount every number of months or years or whatever it is, on top of the interest. You keep on putting money in, right? All right, so what's B3? Take this whole mess, multiply it by 1.05 and add on 1,000. Okay. Let me stop at B2 because I'm running out of room. Isn't that a geometric sequence? Series, because I'm adding them up. The first term is 1,000. How do you get the next term? Multiply by 1.05. How do you get the next term? Multiply it by 1.05. How do you get the next term? Multiply it by 1.05. That's geometric, isn't it? A times R squared. There it is. Okay. So how much money do I have? Remember the rule. It's going to be A times 1 minus the common ratio. A is 1,000, right, the first term? Who's the common ratio? Who's R? I'm doing this. A times 1 minus R to the n plus 1, right? So A was 1,000, is that okay? The first term. Who's R? 1.05. To the how many? How many terms are there? How many terms are there? I started at 0, 1, 2. It's really not 2, it's n plus 1 is 3, right? Over 1 minus R. If our rule that we made up works, this amount and this amount are the same. I'm just testing my rule. Okay? So how much money do I have after 2 years? Let's see. Let's do that on Ziggy. Where are you, Ziggy? Come back. Let's do it this way. And let's do it this way and see if we get the same thing. Okay? All right, second quit. All right, so it's 1,000 plus 1,000 times 1.05 plus 1,000 plus, times 1.05 squared. Is $3,152.50. Is that the same thing as this? Notice what I did was I just plugged this in, right? Now I'm going to plug this in and see that it's the same thing. I'm just confirming this rule for you. All right, so let's plug this in. It's going to be 1,000 times 1 minus 1.05 cubed That's the numerator, so close the parentheses, divided by 1 minus 1.05, or negative 0.05, right? But whatever. Do we still get $3,152.50? We do. Okay. So an annuity is a geometric series. That's why you can predict ahead of time how much money you're going to have at the end of 30 years or something in this annuity. All right, so let me ask you that question. What's B30? Whoa, where are you? I'm going to be here. Let's find. All right, so how much money am I going to have after doing this for 30 years? It's going to be, the first term is still how much money putting down every year, right? 1,000 times 1 minus R. R is still 1.05 to the n plus 1. What's n plus 1? 31. Over 1 minus R. Or in this case, negative 0.05. Negative 1/20th multiplied by negative 20. Divide by negative 1/20th and multiply by negative 20. Okay, so let's see what we get. This was, I didn't finish, $3,152.50. And this is also. So what is it after 30 years? Well, let's do that on Ziggy. Ziggy, come back. Where'd you go? All right, so what the heck is that? All right, so you know what? I'm just going to do second enter and change what I got to change. I'm going to change this to 31. That's it. That's the only difference, right? So instead of messing up what I have here, I'm going to do second delete as insert, put a 1, okay, and then hit enter, and I ended up with $70,760.79 because they'll round up in your favor at the bank to cents, right? It's got to be two places in this case, right? So, I did something different. All right, so 70,760 and 79. 70,760 and 79. I'm going to say that's an approximation because I rounded off to the nearest cent. Okay? So that's an example of a finite geometric series. Okay? Finite geometric series. It's got to converge. You're only adding up 30 terms or 5 terms, whatever. It's got to converge. But what about an infinite series now? All right, let's go back to the infinite series. Here is Zeno's paradox again. And here is the Caliph of Baghdad problem again. Now, if you do this forever, notice I'm not going up to 2 or to 30, I'm going to infinity, okay? Didn't we do this infinitely many times? Didn't we talk about this last time? We graphed it and we got a convergence. What was it for the first one? No. Well, the terms are going to 0, yes. Well, that's a good point. The terms are going to 0. 1/2, 1/4, 1/8, they're going to 0. 1/16, 1/32, 1/64, right? They're going to 0. And we figured out it added up to what? That was the 1, right? So this one I know it converges. How about this one? If I add up infinitely many terms like this, 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64, they must diverge. The numbers are getting so big so fast, there's no way you're going to get a convergent answer. We just stumbled upon 2 things. When does a geometric series converge? And Cauchy's minimal criterion for convergence. I like. Cauchy was a big French mathematician that studied all this kind of stuff. All right, look. If I write this more in general, I say, okay, it's sigma a r to the n, as n goes from 0 to infinity, is a plus ar squared plus forever equals a times 1 minus r to the n plus 1 over r 1 minus r. Okay. But what if n goes nuts? It goes to infinity. Like I'm saying here, it's going to infinity. When does it make sense to take an infinite power of a number? Notice if I add up numbers that get bigger and bigger and bigger, it's gotta blow up. If I add up numbers that get smaller and smaller and smaller, specifically going towards 0, it's gonna add up to something. The divergence test says that a series cannot converge if the terms don't go to 0. If the limit of the sequence, before you add up the terms, if the limit of the sequence isn't 0, forget it. Don't bother adding them up. So this doesn't pass the divergence test. It diverges. This passes the divergence test. It converges. I know, doesn't it sound weird? It's also known as Cauchy's minimal criterion for convergence of sequences of positive terms. But I have a better name for it. Are you ready? Snowball's chance in hell theorem. Are you ready? The Snowball's chance in hell theorem says that the series has a snowball's chance in hell of converging if these terms don't go to 0. If the terms go to 0, it may converge. If the terms don't go to 0, they cannot. Okay? So what does R have to be so these terms get smaller and smaller and smaller? No, not 0. Here R is 2. That was bad. Here R is a half times a half times a half times 2 times 2. Has to be less than 1. Okay. If you take a number less than 1 and you take powers of it, bigger and bigger and bigger up to infinity, what do you get? 1/2 squared, 1/2 cubed, 1/2. This goes to 0 in the limit. If R is less than 1, this becomes 0. So what's 1 minus 0? 1. Done. The sum of an infinite geometric series is A, the first term, over 1 minus R, the common ratio, if R, in absolute value, is less than 1, because it works also for if R is like negative a half. That would work too. Any R value less than 1 in absolute value, negative a half, positive 2/3, positive 1/2, negative 3/4, any number less than 1 in absolute value will work this way. Okay? So this is what a finite geometric series converges to. This is what an infinite series converges to, A over 1 minus R. That's it. As long as R is less than 1 in absolute value. So for example, here, let's try that out. We said we knew this is 1. Didn't we get that graphically? We said it looks a lot like 1. Or we did a convergence table and eventually got 1.000, right? And we said we only said this. We could only say this, remember, with fix 4? I'm going to say this exactly now. Why? Because what's A up here? It's the first term, 1/2. And what's R up here? It's also 1/2. So you get A, which is a half, over 1 minus R, which is a half. 1 minus a half is a half. A half over a half is exactly 1. Not approximately 1, exactly 1. It is exactly 1. So not only can I figure out when an infinite geometric series converges, but what it converges to. Okay? Questions how that works? Let's practice that up. It's going to become important because there's going to be some other series that we don't know whether they converge or not. We're going to use series that we do know whether they converge or not to compare them to see if they act like this. Okay? We're going to be using something called the comparison test. So we need like a little grad bag. We need a little like toolbox of series that we know to converge or diverge. So an infinite geometric series converges to this if R is less than 1 in absolute value. And it diverges if R is not less than 1 in absolute value, like R is 2. A was 1, R was 2, multiplied by 2, multiplied by 2, right? A is a half, R is a half, multiplied by half, multiplied by half, right? All right, let's see. Take a look at questions from the homework page for 9.2 on geometric series. Page 448, I think. Yeah. Take a look at, say, number 1. Straight from the homework tonight. Page 448, number 1. says, decide which of the following are geometric series. For those that are, give the first term and the common ratio. And for those that are not, say why not. And if, by the way, if they are, what do they converge to if they converge? All right, so number one says we got 2 plus 1, whoops, plus a half, plus a quarter, plus an eighth, plus a, sorry, yeah, that's it, plus it, all right, forever. Would you classify this as geometric? If so, who's A? 2, who's R? It's a half, right? It's almost the same series we had a minute ago, except it started a few terms earlier. Okay, so it is geometric. You know A, you know R. Is R an absolute value less than 1? So is it convergent? What does it converge to then? A over 1 minus R is 4. That makes sense. Didn't we just add up this much and we got 1? What did we do? We just added 3, so we got to have 4. Are you happy with this? This is A, the first term. This is R, the common ratio, times a half, times a half, times a half. Okay? So we know when a series of constants, when it's geometric, and when it converges, and what it converges to. Okay? That's good to know. All right, how about number 2? Now I got 1 minus a half, plus a quarter, minus an eighth, plus a 16th in that pattern forever. Is that geometric? What do you think? Yeah. If so, who's A? 1. Who's R? Negative a half. Okay, that's fine. So let's see, what does it add up to? Now, that R, that negative 1/2, is it less than 1 in absolute value? So the series has to converge or not? Yes, okay. So what does it converge to? You tell me what's right here. 1, that's the A, over what? 1 minus who? Negative a half. Don't forget, how do you subtract the negative? You add a positive. So this is really 1 over 3 halves. How do you divide by 3 halves? You get 2/3. So if I graph this on the calculator, it will approach a horizontal asymptote of y equals 2/3 eventually. Okay? 1.5, 0.75, something less than the 2/3, something more than 2/3. It's going to get closer and closer and closer to 2/3, 0.6666. But anyway, this gives me the answer exact. Whoops, what happened there? So that's fine, I'm done. I don't need the calculator. Everyone happy how we got 2/3? You know if it's geometric or not. You know if it's convergent or not. You know what it converges to. This is important. Let's practice this up here. How about 3? 1 plus a half plus a third plus a fourth plus a fifth. Geometric? Yeah, who's A? 1, who's R? What times 1 is a half? A half. So you got to be able to multiply by a half again. No, not geometric. So I don't know if it converges or not because I only know about geometric series that converge. This may or may not converge. Does it pass the snowball's chance in hell theorem? Are the terms, before you add them up, the numbers that you're adding up, are they getting closer and closer to 0? It has a snowball's chance in hell to converge, but guess what? We're going to find out in a little while. Nope, this one blows up. Anyway, 4. Because that's a famous series too. We're going to get to that. What about this one? 5 minus 10 plus 20 minus 40 plus 80. Geometric or not? Yeah, who's A? 5. Who's R? Negative 2 times negative 2 is 10, times negative 2 is 20, times negative 2 is negative 40. Right? Okay, good. Is it a convergent geometric series? No, because the negative 2 in absolute value is 2. Is that less than 1? No. So yes, it's geometric, but no convergence. Not convergent. Yes, geometric. Okay? They wanted to know, is it geometric or not? And then, is it convergent or not? And I added, if it's convergent, go ahead. Figure out what it converges to. This one was no not geometric. And by the way, not convergent, but you don't know that yet. So that's top secret, don't tell anybody. You don't know why yet, we'll see. All right, how about 6? Now what's different about 6? Look at this. 3 plus 3z plus 6z squared plus 9z squared, cubed is it? Plus 12z to the 4th. What's different here is that you don't have a series of constants, you have a series of power rules or polynomials. That's not a series, that's a power series. But what if I let this be f of z? Some function in z. What if I plug in z as 1, for example? What's f of 1? Just plug in 1 everywhere, right? 3 plus 6 plus 9 plus 12 plus... So now you know why we study series of constants before we study power series. Because to know whether a power series works, it actually is a function, we have to know if when we plug in numbers, we get convergence. When we plug in a number into the z's in this power series, you end up with a regular series. And if this regular series converges, then that series converges. That's next week. That's this week. If I ask you if this is geometric, what would you say? Is this geometric? No. So that can't be. So not geometric. Okay. Try that again. 7. 7 says 1 plus 2z plus 2z squared plus 2z cubed. Whether I plug in 1 for z or not, can you tell whether it's geometric? Yeah, who's A? 1. Who's R? 2z. Okay. So what does it add up to? What goes on top? A, which is 1 over 1 minus r, which is 1 minus 2z. Only if r in absolute value is less than 1. Guess what you just proved? When a power series converges, it converges to a function. So if, say, this is something you want to integrate, and it's a pain in the ass, you can't do it. Guess what? This is easy to integrate instead. They're equal. Use this instead. That's chapter 9. That's what we're going to be doing. We're going to be using power series to make integration easier, to solve differential equations easier, that kind of stuff. So we're, in chapter 10, we're going to figure out how to start with the function and get its power series so we can integrate this instead of this if this is impossible. This isn't impossible, though. What if I was integrating this? Do you know how to do it? Is it a U sub? Is it a by parts? Is it a partial fractions? That's the question. And if you can't, can you integrate this instead? Well, yeah, sure, it's power rule. That's easy. But don't we know how to do this one? U is what? 1 minus 2z. So du is negative 2dz. So I hate when it does this. Why is it doing that? There's too many controls on this stupid thing. There's a way to change your pen over here, and there's a way to change your pen on the button here. I keep on hitting this stupid button. All right, so replace dz with what? Negative 1/2 of du. So this is negative 1/2 du over u. Do you know how to integrate 1 over u to u? How? ln absolute u. So you end up with negative 1/2 the ln absolute 1 minus 2z plus c. So this is not a question that you would do this way. But if you couldn't do this, that's another thing to integrate instead. This is easy to integrate. All right? This is just 4z squared. How do you integrate it? 4z cubed over 3. This is just 8z cubed. How do you integrate it? 8z to the 4th over 4. This is easy to integrate. If this is impossible, do this. Okay? That's where we're headed. Okay? That's next week. All right. So I didn't talk about this because if I told you about this top secret stuff we're doing next week, then I'd have to shoot you. All right. So if you graph this mess and you graph this mess, they're going to look the same, only on this domain. That's the point. Notice what this domain is. it says that 2z is between negative 1 and 1. So what does that mean z is? How to get rid of the 2? Divide by 2. So z is between negative 1/2 and positive 1/2. So if I graph this in function mode with x's, okay? It doesn't have to be a z. If I graph this in function mode as y1 with an x, and I graph this in function mode as y2 with x's, right? They're going to match only when x is between negative 1/2 and 1/2. That's what that said, okay? Because it's a geometric series that converges to that only then. But not only is it a geometric series, it's a geometric power series. That's big stuff. That's going to be next week, okay? So we're not doing this for nothing. And remember, that what we're doing today is not on the test tomorrow, but we got to do it. Sorry. We don't have time to do it otherwise. All right, let's practice this up a little bit more. Number 8 says y squared plus y cubed plus y to the 4th plus y to the 5th and so forth, right? Is that geometric? Yeah, because a is y squared and r is y. So it adds up to what? What goes up here? Y squared over what? 1 minus y squared. Y, right. R is just y. But that is a true statement only if y, the value of r, is less than 1 in absolute value. Okay? For y values between negative 1 is what that means. Negative 1 and 1. Okay? Again, if I graph this and I graph this, I'm going to get the same thing only for these values. But wait, this is easy to graph. You can put this into y1, right? In function mode, it would be x squared over 1 minus x, right? You can do that in function mode. How do you graph this? It goes on forever. How are you going to do that? You can't even type it in. Say again.
What if it's why is only like
Well, because we proved back here. Where the heck was it? Come on. Oh boy, it was way back. We proved that an infinite geometric series adds up to a over 1 minus r only when r is less than 1 absolute value, because then this term goes to 0. That's why. And that's the r. The y was the r. Now I gotta go find this crazy page. What the heck page am I on now? Come on, today. Holy cow. Okay. Okay, number 9. So knowing about geometric series of constants, you can already do some power series stuff. 1 minus x plus x squared minus x cubed plus x to the 4th minus, okay? Is this geometric? Yes. A is 1, R is negative x. So this adds up to what over what? 1 over 1 minus an r, which was negative x, so 1 plus x. This is only valid if r in absolute value is less than 1, which is the same thing as this, which is the same thing as this. All right, so the stuff we're doing today and we started yesterday is getting you ready for stuff for next week. You're getting you ready for power series. That's the point. Now, just for fun, can we graph that and see if it's true? For those x values between negative 1 and 1, those two graphs should be the same. All right, let's see. All right, so go over here. Let's graph 1 over 1 plus x. Let's see what that looks like. Let's start with that. I'll go into y equals. Now I'm in sequence mode, so I got to change it back to function mode. All right, so I'm back in function mode. And so I'll clear that, and it's 1 over 1 plus x. Okay, so 1 divided by the denominator in parentheses, 1 plus x. How about a zoom 4? And you see there's a vertical asymptote at x equals negative 1 because it's not defined at x equals negative 1, is it? Okay. Now, but the point is that this thing, when I graph it, is going to match this curve only on these x values, at best. That's if you add up infinitely many terms. forever. That's the best scenario. All right, only from x equals -1 to +1. So only this piece of the curve is going to be valid. Is that true? Let's see. Let's go to y2 and graph this thing. I'm going to say, okay, how about 1 minus x? Just that much, just two terms. See what it looks like. Okay, it's a tangent line at x equals 0. What do you think is going to happen if I add on the x squared? That's going to give you some curvature, concavity. Okay, let's add on the next term, 1 minus x. Whoops, dang it. 1 minus x plus x squared. Let's see what that looks like. Here's the curve we're trying to get. Let's see how much of it we get. You see that this parabola, that's y2, matches the curve for more than just at x equals 0, but a region near x equals 0, a neighborhood near x equals 0, between -1 and 1. Imagine that. Add on another term. What's the next term? Minus x cubed, right? Minus x cubed. Graph that. Now we're going to get a cubic that's going to act more like the curve for more values of x. Here's this cubic. That's y2. That's everything up to here. And it's matching the curve for more values of x. Do you see the point? If I keep on doing this, more and more and more terms, it's only going to work between -1 and 1. It's never going to work beyond 1. It's never going to work beyond -1. Okay? So that's the game we're going to be playing next week, so we can figure out how to integrate stuff that may not be easy to integrate otherwise. Any questions up to here? All right, that's everything you need to know in 9.2 geometric series. I think it's a good place to break. Unless you have a question, anyone? We're good? Or we'll break for about 5 minutes, come back, we'll go to 9.3. When do other series converge? We know when a geometric series converges. Now let's talk about other series after 5-minute break. Because that was the numerator, so you parentheses, second parentheses, and then the denominator too, second parentheses. And we had some negative y, negative 40. Division comes up, and some below, so we're going out. Be careful with complicated fractions. The numerators, plain sick, put them in parentheses and the denominators too. That was the second one because we started at 0, yeah. Yeah. Just found out somebody's been putting my mail in the wrong mailbox. I haven't been getting mail for like a week. Where's the mail? There's this pile of mail in somebody else's mailbox with my name on it. Oh, God. Oh, now you tell me. No. No. There's stuff in my folder for 10 other people. What the heck is going on? Uh-huh. Something interesting. Hang on just a sec. What the heck? Am I getting stuff for Christmas now? What is this? Oh, really? That's cool. Alright. Yeah, that's a little late. B130 Math Center, yeah, but it's spring. Okay, let's look at that. Hang on, I'm not done with just a minute. What the hell is this? Yeah, whatever. Not in. Yeah, too late. No. No. Did. Okay. Something. Look at this later. What the frick is this? Now they tell me this. What, there's more? Yeah, I know. Whatever. That's nice. The heck is this? What? No. What is that? I'll have to look at it later. Alright, so this is relevant, this is not. Filing system. Circular filing. Actually, square. Okay, so we'll continue. You ready? Yes, no, maybe? Alrighty, here we go. If it's not geometric, how do you know if it converges or not? Well, let's try this. We're in 9.3 now. Let's use something called the integral test. Okay? Let's see if this series converges. Now, we mentioned this series a little while ago. Can I start at n equals 0? Yeah, really? Why not? It's undefined, 1 over 0, right? So I'm going to start with 1. And so who is this series? It goes, what's the first term? 1 plus a half plus a third plus a quarter and so forth, right? Okay. Um, How do you know if that converges or not? Well, if you take a look at a left 3-month sum. Let's say we graph that. 1 over x looks like this instead of 1 over n, 1 over x, okay? And we start at x equals 1, right? Let's say I want the area under this curve using a left 3-month sum with some delta x. Let's say delta x is 1. And so forth. Do you see that the area under the curve, the area of these rectangles, isn't that these numbers? 1, I have a delta x of 1 and a height of 1. I have a delta x of 1 and a height of a half. This function is 1 over x, and x is 2, that height is 1/2, right? I have a delta x of 1 and a height of 1/3. You see what I'm saying? These rectangle areas are these numbers. If I add up the areas, aren't they bigger than the area under the curve? Right? Okay, so what I'm going to do is I'm going to say, let's take a look at the integral, the area under the curve. If the area under the curve exists, so does the function. Maybe that's not so obvious. Maybe we should do it this way. Let me try it this way. I don't think a left sum is that good. Wait, let me try that again. Let me try a right sum for this. Let's try right sum. Make it more obvious. If I do a right sum, then the numbers that we're adding are... No, that was a good... No, dang it, that was a good... I'm sorry, that was a good diagram. All right, all right. The idea is this. If the area under the curve exists, then if the area... this area is bigger than the area under the curve, isn't it? Overestimate, right? What if the area under the curve doesn't exist? What if the area under the curve is unbounded, blows up? What does that say about this area which is bigger? It doesn't exist either, it's worse, right? All right, so that's what I'm going to do. I'm going to convert this series into an integral. I'm going to find the area under the curve, and if the area under the curve exists, so does that area. And if the area under the curve doesn't exist, neither does that area. Do you see the game plan here? All right, but this is only true if the following is met, okay? You change your discrete function in n into a continuous function in x. All right? 1, it's got to be a continuous function. No discontinuities, none of that stuff, right? From 1, let's say from 1 to infinity. 2, this thing has got to be decreasing. In other words, the derivative is negative. And 3, the limit as x goes to infinity of the function has to be 0. Now, usually decreasing means that the derivative is negative. There are other ways of doing that, but all right, let me focus on that. F prime is less than 0. Okay? If those 3 criteria are met, and you then do the improper integral from 1 to infinity of that function. If this area exists, this sum exists. If this area does not exist, this sum does not exist. Okay? That's the integral test. Are you ready? Do you remember how to do these? What's weird about this integral? It's, what's bad? It's improper, right? What kind? A, B, or C? B. So you rewrite it as a limit, as x, not x, as who? As b goes to infinity, the integral from 1 to b of 1 over x dx. Now, do you know how to anti-differentiate 1 over x dx? ln. So you're going to write the limit as b goes to infinity of ln absolute x evaluated from 1 to b. Okay, so what is that? That's the limit as b goes to infinity of ln absolute b, but b is positive, so the absolute value is optional, minus the ln of absolute 1, again, the absolute's optional, but ln of 1 is just 0. And what's ln of b as b gets humongous? That goes to infinity. So does this limit exist? If this limit does not exist, this series does not exist. Remember, the series is just the whole sum. Okay? By the way, this is a famous series. It's called the harmonic series. It comes up a lot. The harmonic series does not exist. Okay, let's change that up a little bit. What if I tried a different series that I don't know whether it converges or not? In other words, it's not geometric. Okay? And let's see if I can apply the integral test again. Okay, the first term is 1. What's the next term? What's the next term? Okay, get the idea? 1/16th, 1/25th, and so forth. Okay? All right. So this is a series with all positive terms. Does it meet the criteria for the integral test theorem? 1, if I make f of x equal to what would it be? What did we do last time? F 1 over n became 1 over x. So 1 over n squared becomes 1 over x squared. Okay. Is it continuous? Is there anywhere on the domain from 1 to infinity where it's undefined? 0, but from 1 to infinity, it's okay, right? 1 to infinity is okay. All right. 2. Is f, what is f prime, by the way? How do you differentiate 1 over x squared? Remember what that is, really. It's x to the negative 2. How do you differentiate x to the negative 2? Negative 2 times x to the negative 3, right? Is that always negative from 1 to infinity? Or if not always, for infinitely many numbers from 1 to infinity. It doesn't have to be 1 to infinity. It could be 5 to infinity. Is this always negative for these numbers? It is, because this is negative, and this is just whatever sign you started off with. They're positive. X cubed, if x is positive, x cubed is still positive. So this is negative. Good. It's continuous. The derivative is negative, so the function is always decreasing. And is the limit, as x goes to infinity, of the function we created, is that 0? That's obviously 0. It just gets smaller and smaller and smaller and smaller and smaller and smaller. Okay. So it meets the 3 criterion of the integral test theorem, or the 3 antecedents. Okay? So what does that mean? If the integral from, well, 1 to infinity of who? 1 over x squared dx. If that exists, so does that. Now, they're not the same. If I get like 2 here, it doesn't mean that's 2, right? Okay. So, let's do it. You rewrite this as the limit as b goes to infinity, the integral from 1 to b of x to the negative 2 dx, because you know the power rule for integrals, right? So that becomes the limit as b goes to infinity of x to the negative 1 over negative 1, which is just negative 1 over x, really, right? I'm going to write it that way. Negative 1 over x. Evaluated from 1 to b. Okay, so do so. What's the limit as b goes to infinity of negative 1 over b minus is plus 1 over 1? Does that limit exist? It does, because negative 1 over b, as b gets humongous, this gets closer and closer to 0. So what's the answer? 1. This limit exists. Remember, this is really a limit, right? This limit exists means this exists. What it is, I don't know. It doesn't add to 1. It ain't 1. Because remember, these were the rectangles you get with the delta x of 1 for the left sum or right sum. It wasn't the same as the area under the curve, right? It might be an underestimate or an overestimate. It ain't 1. But since this exists, so this converges. Check. It converges. This one, did I say, I should say diverges. How about that? Diverges. Okay? So this one diverges, the harmonic, and this one converges. Yeah.
But one of those things, if it's not continuous, then you go on.
Then you can't use this test. Yeah, you can't use this test. Um, well, yes and no. Say it's not continuous somewhere in between 1/9 and 1/16, let's say. You could drop a finite number of terms, ignore them, and figure out whether infinitely many, the tail of this series that goes on forever, if that converges, then you're okay. You can chop off, a finite number of terms, and then the rest of the series still converges or diverges the same as it did. So if there's a problem somewhere in between, just start after that. You could do that. Yeah, that's possible. All right, now, do you recognize this integral? We did this integral a while back. We called this a p integral, where p was 2. Guess what you just figured out? P series converge when p is greater than 1. Remember we figured out when it was greater than 1, the integral converged to 1 over p minus 1. And if it was less than 1, a positive number less than 1, like a half, it converges to 1 over 1 minus p if you're doing the area from 0 to 1. We're not doing that. We're doing the area from 1 to infinity. So p integrals converge from 1 to infinity when p is greater than 1. So I could do this, I could do the exact same argument if I had cubic here and a cubic here. I would get an answer here and I would get convergence here. Fourth power here, I'd get an answer here and convergence there. And so forth and so on. If this is 4, you get 1 over 4 minus 1 is a third. If this is 3, you get 1 over 3 minus 1 is a half. If this is 2, you get 1 over 2 minus 1 is 1. Remember p integrals? We wrote this down somewhere. P integrals from 1 to infinity converge to 1 over p minus 1 when p is greater than 1. So the integral we just did has to be this. Because p is 2 is greater than 1. So therefore, this p series exists, or does converge. That there is a sum. What it is, I don't know. Well, actually, I do know. This is actually a famous result. Remember Euler? How do you spell Euler? We named the number E after him. How do you spell Euler? E-U-L-E-R. Right. He came up with this result using rectangles. Nobody knows how the freak he did it. It's in one of the books he wrote. He never proved it in that book. He proved it somewhere. He said, oh yeah, geometrically I drew rectangles and stuff. It is correct. How the hell he did it in 1729, whatever the hell it was, without calculators, nobody knows how the hell he got that answer. But that answer is exactly correct. This is called Euler's series because that's a famous result. Okay? In fact, there's $1 million question. You might want to go to claymath.org. It's a website, claymath.org, where they have the top 10 most famous unsolved problems in mathematics. And one of them involves this limit. If you can prove that this limit exists for any p, where n is a complex number, then you've proven the Riemann hypothesis, which says that prime numbers are predictable based on these weird areas. It's an area, isn't it? If you think of it as rectangles. It's a great unsolved problem, and if it were solved, then you could figure out big, huge prime numbers really easy. That's a hard problem. Do you know prime numbers? What are they? What's the smallest prime number? 2. It's a number. It's an integer that's only 2 factors, 2 unique factors, 2 different factors, 1 in itself, right? What's the next one? After 2? 3, 5, 7, 11. After a while, they get farther and farther and farther apart and harder and harder and harder to find. There's a website called the Great Internet Mersenne Prime Search, which has just published the largest prime number known. It's 2 to the 2,156,218 minus 1. It's a ginormous power of 2 minus 1. It's over 10 million digits long. How do you find the next one? That's a big problem. By the way, if you find the next one, Obama will go and knock on your door, give you $1 million, maybe buy you a tropical island to retire on, and say, oh, you know that prime number you just found? Don't tell nobody, I'll take that. Why is this such a big deal? The biggest prime number known to man. Why is this a big deal? Anyone know? Because they use that number that nobody knows, which is really hard to find, it's ginormous, for encryption of top secret stuff. So like the war zone in Iraq or something. I'm not talking about 128-bit encryption on the internet that you can break in 2 seconds. This is ginormous encryption, impossible to break, unless you know the key, this insane prime number that's 10 million digits long. It's an exact calculation, 10 million digits long. When was the last time you did arithmetic? Add, subtract, multiply, divide, where the digits were 10 million digits long, where the numbers were 10 million digits long. That's a tough thing to do. You can't even do that on a Ziggy. You can't do that on a HAL either. You can't. It's impossible. HAL can actually do some pretty big integers, but only up to 400 digits. 400. I'm talking about 10 million digits or more. Yeah. It's been tried, and it ain't happening. This is uncrackable, unless you know the key. Unless you know that prime number they're using. The prime numbers that they're publishing on the Great Internet Machine Prime Search, that's not the biggest one. There is another one that Obama knows, and nobody else knows, okay? Just watch. And if you find it out, guess what? You're going to go disappear one day when the CIA finds you. And it's like, wait, where did he go? I don't know. That's basically the password, yeah, to like the entire Pentagon. Yeah, I've said too much. Okay, so anyhow, so that's the integral test. Okay, any questions how that works? So now we know geometric series that converge, and we know p-series that converge. We also know geometric series that don't converge, and we also know p-series that don't converge. Look. That was not me, was it? Did you hear that? This happens every night. All right. Here is a geometric series. Does it converge? Yeah, that is me. Shut up. I'm not talking to you. It's talking to me. Okay. Stupid feature. When it's low on power, it starts talking. That makes sense, right? That uses more power than anything. Anyway, so it's just stupid. Yeah, but it's just going to die anyway, so I don't care. Is that geometric? Yeah, what's the first term? 2/3. What's the next term? 4/9. What's the next term? 8/27. Actually, this is I should say plus in between, right? I'm adding. Plus 2/3 squared is 4/9 plus 2/3 to the third is 8/27 plus so forth, right? So who's A? Who's R? It is 2/3. So this becomes A over 1 minus R is 2, right? Okay. Why? Because R was less than 1. R is 2/3. First term is 2/3, but you get the next term by multiplying by 2/3, and multiplying by 2/3, and multiplying by 2/3. So R is also 2/3. So it's A, which is 2/3, over 1 minus R, which is also 2/3. 1 minus 2/3 is 1/3. How do you divide by a third? You multiply by 3. The 3's cancel. You get 2. All right. That's a geometric series that we know converges, right? How about this one? It's a geometric. Yeah, A is 3/2. Yeah, R is 3/2 too. Does it converge? No, because R is 3/2, which is not less than 1, so divergent. So we have an infinite set of convergent geometric series, as long as this is less than 1 in absolute value. We have an infinite set of divergent geometric series, as long as this is an absolute value bigger than 1. We also have an infinite set of p-series that we know converge or not. Does this one converge? Does it converge? Remember this, I'm going to use the integral test from the integral from, as the limit as b goes to infinity, the integral from 1 to b, of 1 over x cubed dx, right? Remember, p integrals converge to 1 over p minus 1 when p is greater than 1, right? So the integral will come out to 1/2. So since the integral exists, the series exists. I don't know what it converges to, but it converges. As long as this is bigger than 1, 2, 3, 4, 5, 12, 1.5, 2.3, anything bigger than 1, right? That's an infinite set of series I know to converge. How about this one? That's a p-series. What's p? 1/2. Is that a good p? Here we said p was good because it's what? We're in 1. This p is what? 1/2. Is that good? No. We have an infinite set of p-series that diverge too, as long as the x1 here is less than 1. Positive, but less than 1, like a half, like a third. This is a half, right? I can make it a third if I want. The cube root. A fourth, a fifth, whatever. Anything, they're all the p's are positive. But less than 1, diverges. More than 1, converges. What it converges to, I don't know. Actually, there is a formula. Remember Euler's thing? There is a formula that extends Euler. For even powers, it's known. For odd powers, it's not known. The exact answer of what it converges to. All right, so look, we got a whole grab bag of stuff here. We have convergent, a whole ton of convergent geometric, a whole ton of divergent geometric, a whole ton of convergent p-series, and a whole ton of divergent p-series. And by the way, this is one of them. This is also a divergent p-series because p is what? 1. Remember who this is? That's that series called the harmonic. The harmonic comes up a lot. The harmonic diverges because it's a divergent p-series. Okay? It's a special case of this argument here, where p is not greater than 1. It is 1. Bad if p is 1, bad if p is less than 1. Good if p is more than 1. Right? So this is bad because it's not more than 1. It is 1. N to the 1, right? And remember, we proved that was bad with an integral test, remember, with the LNs and everything? So you've got a huge grab bag of stuff to choose from to compare to other series that you don't know whether they converge or not. And you can always use the integral test when you're stuck, if you're stuck, though. Okay. All right, how about on the homework page for this section 9.3, page 454? Let's say number 2, which says the series, as n goes from 1 to infinity, of n over n squared plus 1. Okay. Can we use an integral test here? Well, let's see. 1, f of x would become what? X over x squared plus 1. Okay. Alrighty. Is that continuous for all x from 1 to infinity? Yeah. Okay. Nothing weird. No discontinuity. 2. Is f prime negative? What's f prime going to be? Low, d high, minus high, d low, over low, low. Now, low, low is a square. So that's always positive, right? The denominator is always positive. I want to know if this thing is negative. So I really only care if the numerator is negative, really. Let's clean up the numerator a little bit. This is going to be 2x squared minus 2x squared is negative x squared. So you got 1 minus x squared over x squared plus 1 squared. Is that always negative for x Greater than or equal to 1? 1 to infinity? Yeah. Plug in greater than 1. If you plug in 1, it's 0. But greater than 1, like 2, that's negative, right? Okay. And 3 is the limit as x goes to infinity of our f of x is at 0. Yeah, because as x gets humongous, this 1 really is immaterial. It acts like x over x squared, which is like 1 over x. And 1 over x goes to 0. So the 3 criteria of the integral test are met. So that means you can prove divergence and convergence of the series based on convergence and divergence of this integral. Okay. Equals the... You know, I'm going to go to the next page. I'm running out of room. Okay, so first of all, it's improper, so rewrite it as a limit. As who goes to what? B goes to infinity. The integral from 1 to b of this mess. Okay, what kind of integrating are you going to do here? Trig sub might be useful, but I think it's a u sub will be easier. U is, if u is x squared plus 1, let's see, if u is x squared plus 1, du is 2x dx. So replace x dx with 1/2 of du. So this is 1/2, 1 over u du. How do you integrate 1 over u du? ln. So it's the limit as b goes nuts of 1/2 the ln of absolute u. This is u, isn't it? And absolute doesn't really matter here because this is always positive, but whatever. Evaluate it from 1 to b, and you get the limit as b goes to infinity of 1/2 the ln of absolute b squared plus 1 minus 1/2 the ln of absolute ln, of ln absolute of 1 squared plus 1, which is 2. That's a 2. Okay, so the question remains, does this limit exist? This is a constant, so that's not a problem. Does this limit exist? No, as ln of x, as x goes to infinity, ln of x goes crazy. Ln of x squared, forget about it. Does not exist. So, diverges by integral test. Okay? Questions how we did that? Alrighty. Try another one like that. Number 4. Sigma. N starts at 2, goes to infinity, of 1 over n times ln n squared. All right, let's try the integral test again. That's what this particular unit was about. So, 1. F of x becomes what? Simply replace the n's with x's, that's all. Make the discrete function in n a continuous function in x. And use what you know about continuous functions. All right, is it continuous for all x from 2 to infinity? Well, notice what's bad. What would make this fraction undefined if n is what? Or x is what? 0. Or if x is, when is ln 0? At 1. But notice 0 and 1, they're not in the domain of the problem. So is it continuous? Yes, it is. Okay, 2. Is the derivative always negative on that domain? Well, what's f prime? Well, low d high minus high d low. Now, d low is a product rule, isn't it? First times the derivative of the second, chain rule, plus the second times the derivative of the first. First times the derivative of the second. U squared gives you 2u du. If u is ln x, du is 1 over x, right? Plus the second is ln squared times the derivative of the first, derivative of x is 1. All over low, which would be x squared ln x to the 4th. Again, low is always positive, So how do I know if this is negative? If the top is negative. What's this? That's just 0. So let's simplify the numerator. We're going to get, I don't know this yet, I'm not saying this yet. Okay, so that's 0, and I get negative 1 times stuff. And what happens with these x's? They cancel. So I'm going to distribute the negative 1 throughout. I'm going to cancel the x's, right? So it's going to be negative 2 ln x minus ln squared x is the numerator, right? Again, the denominator is always positive, so if this fraction is negative, it's because the numerator is. On the domain from 2 to infinity, what's ln? Positive or negative? Remember what ln looks like? That's 1. So from 2 to infinity, for x is 2 to infinity, the y values are all positive. What if I multiply by negative 2? That's always negative. What if I square something? It's always positive. What if I subtract it? It's always negative. That numerator's got to be negative. So the whole thing's negative, right? Because the denominator is positive. So that's a true statement. And 3 is the limit as x goes to infinity of the function is at 0. This is what I call bottom heavy. It's a constant over humongous. Bottom heavy, 0. Yeah. Right? Okay, so all 3 antecedents of the theorem for the integral test are met, so therefore you can apply the integral test. Okay, let's apply. So I'm going to integrate this from 2 to infinity. Okay, so can you integrate that? Yes. You have the tools. You can do it. How? Maybe I should make it more obvious. Let's make it more obvious. Not that obvious. Now it's easy. U is ln. U to the n du. If u is ln x, isn't that du? Isn't the derivative of ln 1 over x, right? So that's u, that's du. So you got u to the n du. How do you do u to the n du? Integrate. U, forget the x's. U to the n du gives you. Or let me make it more obvious, more precise. U to the negative 2 du gives u to the negative 1 over negative 1, or negative 1 over u. Okay. The limit, as b goes nuts, evaluated from 2 to b. Okay. Equals the limit, as b goes nuts, of negative 1 over ln b minus is plus 1 over ln 2. Does that limit exist? Isn't this bottom heavy? This limit is 0, so the whole thing goes to what? 1 over ln 2. This is 0, so that's left. Okay? So this limit exists. This thing is a limit. It exists, therefore this converges by the integral test. Alright, so even if it's not geometric, even if it's not a p-series, I can still use the integral test to test for convergence for weird stuff. At least if it's integrable, if you can integrate it. All right, so that's all there is about the integral test. What happened? Scrolling. Oh, yeah. This part of the next page. Because I was on the other page. The other page? Okay. That one? Okay. Alrighty. How about this one? Okay, this is 9.4, the comparisons. What if the integral test doesn't apply? What if it's not a p-series? What if it's not a geometric series? What if it's not a harmonic? What if it's nothing I know, and the integral test doesn't apply? The f of x you get is discontinuous, or it's not decreasing, or it's not going to 0. Oh, by the way, let me just mention one little thing. This thing about it's the derivative is negative, so the function is always decreasing, and the limit is 0. Remember what that is. That's just a restatement of Cauchy. Cauchy's minimal criterion for convergence of series of positive constants, or the Snowball's chance and health theorem, right? The Snowball's chance and health theorem says this isn't going to add up to anything nice unless the terms are getting smaller and smaller and smaller and going to 0 before you add them up, right? That's Cauchy's criterion, or the Snowball's chance and health theorem, or the divergence test, right? So it's built into the integral test, so it's automatic. Okay, that's good to know. All right, how about all right, this is the comparison test. Let's say I asked you about this series. And by the way, if you try it, it may pass the criterion, the 3 criterion for the integral test, but I can't integrate that. How are you going to integrate 1 over x cubed plus 1 dx? No. Sorry. It ain't even trig sub. It's almost trig sub. If it was x squared on the bottom, you could do an arctan, right? No go. So, what do? How do you know if that thing converges or not? By the way, your last ditch effort is to graph it, see if it converges to horizontal asymptote, right? But I'm saying analytically. Is there some way to do it? And there is. There are 2 more tests I'm going to be talking about. I don't know if I'm going to get to ratio test, but no chance. Comparison test and ratio test, all right? Here's the comparison test. Comparison test says, if you can show that the terms you're adding up in this unknown series are always less than the terms of another series that you know converges, then it must converge too. 1 over n, now be careful, 1 over n, yeah. Doesn't it look a lot like a p-series? In fact, doesn't it look a lot like a p-series that we know converges? Is this a p-series? Is this a p-series that converges if p is bigger than 1, right? Now, is this a true statement? What's the only difference between these terms and these terms? I made the denominator smaller. I took 1 away from every denominator. So I made the denominator smaller. If I make the denominator smaller in a fraction, the fraction itself becomes bigger. That's a true statement, isn't it? That's the comparison test. If you can compare an unknown series to a known series, and that known series is bigger and convergent, this must converge too. Therefore, convergent by comparison test, comparison to a p-series, and what's good about it is that p is 3. That's all you have to say stuff, but that's all you have to say. Okay? So that's the game. The game is this. Make the denominator smaller so the whole thing's bigger, or make the numerator bigger so the whole thing is bigger. Make this bigger, and see that you get a series that you know to converge, then that converges too. Vice versa. What if you want to prove that this diverges? I can't because it converges, but pretend. Let's say this thing diverges. I can prove that this diverges if it's greater than, if this goes the other way, than some other thing that I know diverges, like that. If I could make this statement, then that's how you prove by comparison test divergence. If the unknown series is always bigger than a known series that diverges, if this is divergent and that's bigger, it diverges worse. What does divergent mean? It adds up to infinity, right? So it goes to infinity faster. If it's bigger than a divergent, it's bad. So divergent. If it's smaller, if the unknown series is smaller than a known convergent series, that's convergent. Gotta be. You see the game for comparison test? All right. So, let's see. What's a good way to go with this? Hang on. All right, how about we just go straight to the homework page for this? Page 461. All right, in fact, 461, they start off by giving you little hints. All right, page 461, the homework page 9.4. Number 1 says, does this thing diverge or not? Yeah. 1 over, what is it? 1 over n minus 3? As n goes from 4 to infinity. And they said, hint, 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 use what you know about 1 over n. All right, what do you know about 1 over n? Now let's do it for the same domain. Didn't we prove that 1 over n, the series based on 1 over n, what does it do? Converge or diverge? Diverges, because that's that harmonic thing. That's a p series of p is 1, that's bad. P greater than 1 is good. All right, so now if this diverges, and I want to use it to show that this diverges too, this has got to be greater than or less than? Greater than. Is it? Well, what did I do? I took the negative 3 away from the bottom. What I did was I made the denominators bigger. Didn't I? Because I'm not subtracting 3 anymore, so it's bigger. I'm subtracting 0, say. So if the denominator is bigger, the whole fraction is smaller, so this is valid, yes? Therefore, divergent by comparison. Now you could say to a p series of p equals 1, or to the, actually they get to be a stickler about this, to an harmonic. Why not the harmonic? This is not the harmonic, because the harmonic starts at 1. But an harmonic has to diverge too, because what's the only difference here? I didn't start at 1, so I'm just erasing term 1, 2, 3, right? But if all those terms added up to infinity and I just erase the first 3 terms, is it still going to blow up? Yeah, it has to, yeah. I'm just taking off a finite piece, it still blows up. Now, I'm not going to get like crazy on a test if you do this. You can say the harmonic or harmonic, but they get a little crazy on the, I teach the AP stuff, right? Get a little crazy about this, but whatever. All right, so number 1, they gave you a hint, but hopefully, eventually, you're not going to need a hint. How about number 2? Does this converge or not? N equals 1 to infinity. 1 over n squared plus 2. And they said, hint and hint, you know about n squared, don't you? How do these compare? Greater than or less than? Less than. Is this convergent or not? This is a convergent p series. If p is 2. If this is convergent, these numbers are smaller. When I add them up, they better converge too, right? Therefore, what's your conclusion? The unknown series does what? Converges by comparison test to a p series. And what's nice about the p series is that p is 2. That's the work. That's all there is, the work. I mean, that's it, but you got to do it. Alrighty. How about 7? Next page, 7. The unknown series is n starts at 1, goes to infinity, of n squared over n to the 4th plus 1. Yeah, that's a 4. Okay. Well, they don't give you a hint on this one. So what's your intuition? Does it look like something you know? What? I'm not hearing it. What? No, not 1 over n to the 4th. Exactly. All right, here's the game. As n gets humongous, does the 1 really matter? Right? If n is 1,000,000, you got 1,000,000 squared, or 1,000,000 to the 4th, plus 1. Who cares? So as n gets humongous, this is like n squared over n to the 4th. But n squared over n to the 4th is just 1 over n squared. So there's the intuition. Can you use a p series where p equals 2 again? All right. The idea is you want to make it so that, okay, you want to make it so that this is a true statement. Okay? Right? Is that your intuition? As n gets humongous, it's like 1 over n squared converges, so I want to make this smaller than something that converges, so it converges too. Is that a true statement, though? I don't know, because I replaced the numerator n squared with a 1, and for every n greater than 1, that would be smaller, wouldn't it? That's hard to justify. Let me just Well, okay, let's just look at the bottom. All right, can you do this? If simply just get rid of the 1? What if I just get rid of the 1? Is this a true statement? If I get rid of the 1, the denominator is smaller, so the whole thing is bigger, and that is 1 over n squared. That's what it is. So I just had to fiddle with the bottom. I thought I had to fiddle with the top two. Okay, so therefore, the unknown series, this guy, is convergent by comparison, again, to a p-series. And p-series is nice because p is bigger than 1. In fact, it's 2. Yeah, all I had to do was play with it. I thought it was more complicated. Okay, can I move on? How about 6? Let's try one more like that. 6. 6 says the unknown series that you're testing for convergence is n goes from 2 to infinity of 1 over ln. Okay? And you want to show whether that converges or not. Do you have any intuition what that's like? A series you know. I don't know if this is correct. I'm playing around. Okay, I'm thinking that it's sort of like 1 over n. As n gets huge, this goes to infinity. As n gets huge, this goes to infinity. The fractions that you're adding up are very similar. So what does this guy do? That's the harmonic, or an harmonic, right? So that diverges. So what do I want to see here? You want to see less than or greater than? Greater than. So if this blows up, this is bigger, it has to blow up too? Can you make that argument? Yes, because you know about n Feppel constant. Don't you? No? Remember Long Island Pet? That I don't do acronyms a lot, but once in a while they're useful. Long Island Pet was a nice U choice for biparts, right? Remember that? This is a nice way to figure out if for n going to infinity, which functions overpower which other functions. Okay? This is a constant, any constant like 1, gets overpowered by ln, logs. Logs get overpowered by polys. Polys get overpowered by exponentials. Exponentials get overpowered by factorials, and factorials get overpowered by the unnameable thing. This is the unnameable thing. It doesn't have a name. For example, constant like 2. For example, ln of n. For example, n squared. For example, 2 to the n. For example, n factorial, and the unnameable. See, this has a name. If it's a power where the variable is in the denominator, we call that a power or a poly. But if it's a power where the variable is in the exponent, we call it an exponential. But it's a power where the variable is in both places. I don't know what to call that. But it blows everything out of the water. That comes up sometimes. So is this a true statement? If this fraction is smaller than this fraction, every one of the fractions from 2 to infinity that you're adding up, that means that this denominator is bigger than that denominator. Yes? Is that true? This denominator falls here. This denominator falls here. So was that a true statement? Poly is bigger than log for infinite n. Yes. So if you're stuck in changing the denominator to something smaller or changing the numerator to something bigger, keep this in mind. The higher you're on this list, the bigger it is. Okay? That's a valid argument based on this. This is a proven fact. Don't worry about it. How do you prove that? This has to do with order n in computer science. You don't have to worry about that. So therefore, what's the conclusion? The unknown series does what? Converges or diverges? Diverges by comparison to who? n harmonic, right? It's not the harmonic unless you start at 1. Okay, but just you're chopping off the first term, it's still got to blow up. So if this blows up worse because it's bigger. Why is it bigger? Because this denominator is small, is bigger. If this denominator is bigger, this fraction is smaller. That thing's bigger, it blows up. Okay? So that's the game for comparison test. And if it's really hard to figure out how to make the comparison, this comes in handy. Okay? All righty. One more like that. Number 4. Sigma. N goes from 1 to infinity of 1 over 3 to the n plus 1. Does that remind you of any series you know converges or diverges already? One over 3 to the n. I know that sigma, as n goes from 1 to infinity, of 1 over 3 to the n converges. Why? What kind of series is that? It's not a p-series. We've been using p-series a lot, but that's not a p-series. What is that? That's geometric. First term is 1/3, next term is 1/9, next term is 1/27, right? Equals a over 1 minus r is a half. Yeah, I know this is a geometric series that converges and what it converges to. I don't care what it converges to for this argument. I know that this converges. Now, how does it compare? Is this bigger than that, or is this smaller than that? Smaller. Why? Because I'm just getting rid of the 1 in the denominator, making the denominator smaller so the whole thing bigger. All right, so therefore, what's your conclusion? The unknown series does what? Converges by comparison test to a geometric series. And what's nice about it is that r in absolute value is less than 1 because r is what? 1/3. Right? Isn't it 1/3 plus 1/9 plus 1/27? You multiply by a third, you multiply by a third, you multiply by a third, r is a third. As long as r in absolute value is less than 1, you're good. It could even say negative a third here. Right? That's okay. All right, so that's using the comparison test with p-series and geometric series and harmonic series. Isn't that nice? All right. Okay. One more thing to talk about. The ratio test. Where the heck was that? Okay, yes, there it is. All right, let me ask you this. Does this series converge? You could easily prove that by comparison. Because remember, n Feppel constant, that's a constant, okay? This is the f. Replace it with anything smaller, right? That's bigger, right? Replace it with anything smaller like exponential. If the denominator is smaller, the fraction is bigger. This opens to the larger guy, right? This is smaller. So it converges by comparison test compared to a what? Geometric series with r is a half. Okay, now say you didn't know that. Here's another way to do it. This is called the ratio test. And this works really good when the comparison test fails, especially if you have factorials and or exponentials mixed in here. Okay? This is called the ratio test. Let rho is the ratio, rho is the letter R in Greek, so they call it a rho test. Let rho be the limit, as n goes to infinity, of the absolute value of u sub n plus 1 over the absolute value of u sub n. This also works for series with weird signs and stuff, alternating series, weird signs, whatever. So the absolute value kills off the signs, okay? Now what's u sub n? That's the rule. That's a description of each term. What's u sub n plus 1? That's the next term. Plug in n plus 1 wherever you see n. All right, so what's rho here? It's the limit as n goes to infinity of, now I'm not worried about absolute value now because there's no weird sign, so I'm not going to worry about that, but u sub n is 1 over n factorial. U sub n plus 1 is what? Plug in n plus 1 wherever you see n, so what should I write? 1 over n plus 1 quantity factorial. Now this is what the ratio test says. If this is less than 1, you have convergence. If it's greater than 1, you have divergence. If you get equal to 1, that can happen, the test fails. Try some other test. The test is inconclusive. Doesn't tell you anything. Now remember, a minute ago we proved convergence by comparison test, so this better be less than 1. There are several row tests. Every row test works this way. If rho in the limit is less than 1, you get convergence. If rho in the limit is greater than 1, you have divergence. If rho in the limit is 1, test fails. Okay? Shut up. So, it's still not there, stupid thing. Is it less than 1? I don't know. Let's see. How do you evaluate this limit? How do you divide one fraction into another? Multiply the reciprocal. So it's the limit as n goes to infinity of n factorial over n plus 1 factorial. Do you know what that limit is? Is it in fact less than 1? I know it's less than 1 because I'm 20/20 hindsight. I know it's converging, so it better be less than 1. Is it? Well, what is n factorial? What is like 3 factorial? What is that? 3 times 2 times 1. Okay, so if this is 3 factorial, this is 4 factorial. What's that? 4 times 3 times 2 times 1. What happens if you take 3 factorial divided by 4 factorial? You get 1 over 4. Don't you? In other words, this is the limit as n goes to infinity of n times n minus 1 times n minus 2 times forever, right? But this one is n plus 1 times n minus 1 times n minus 2 times forever down to 1, right? Like 3 factorial is 3, 2, 1. What happens to the n? What happens to the n's? Cancel. What? N minus 1s, n minus 2s, everything all the way down to 1. What's left? 1 over n plus 1. That's what's left. All right. 1 over n plus 1. What's that limit as n gets huge? It's 0. Is that less than 1? Therefore, convergent by ratio test. Because rho is less than 1. Rho is 0, but rho is less than 1. Anything else than 1 is 1. Now remember, this starts off with absolute values, so it's always going to be something positive less than 1 is what you want. It could be 0, it could be 0.2, it could be 1/2, it could be 5/8, but it's got to be less than 1, and it's never going to be negative. Okay, so this is a famous result too. Remember, 1 over n diverged, harmonic, but 1 over n factorial converges. Guess what it is? If you start with n equals 1, you in fact get E. By the way, the sum of the reciprocals of the factorials, infinitely many such reciprocals, starting at n equals 1, gives you E. Is what it is. We can prove that. We're going to prove that later on next week. It'll come up. But take it on faith for the moment. It converges, you know. Yes? I'm saying converges to E. We didn't prove that yet. We will. Okay? So, there you go. Alrighty. So that's useful. A ratio test. Let's try some ratio test questions. How about this is in the same section, 9.4, yeah. So page 462. Whoa, I'm dyslexic today. page 462, number, I don't know, number 39. Oh wait, no, that's not it. I got the wrong thing. Ratio test, ratio test. Ratio test. Wait, I wrote this wrong. Hang on. Number 12, number 12. I'm looking at the wrong thing. I'm going crazy. Okay, there's one test I'm not going to get to. It's called the alternating series test. That comes up next week, so don't worry about it. So you can skip question 40 on the homework. That's the only question on there. But take a look at, say, number 12. It says, sigma, as n goes from 1 to infinity, of to the n factorial over n factorial over n plus 1 factorial. And the idea here, it says to use the ratio test, so there you go. So how do you set up rho? How do you use the ratio test? This has nothing to do with comparison tests, integral tests. I can't integrate factorials. I don't know how to do that. Did we ever integrate 1 over x factorial dx? Yeah. No. All right, so we can't use integral test. I don't know what the hell to compare this to. So ratio test is probably a good way to go. So let rho equal the limit as n goes wild of what over what? On the bottom, you get this. On the top, you get this with all the n's replaced with what? N plus 1. Remember the rule? U sub n plus 1 goes on top, right? Okay. So, what do you get? You got 2. By the way, let me cut to the chase. If I'm dividing by this, right, I'm going to multiply by the reciprocal. You know, so I'm going to write it that way. I'm going to say this. I'm going to say u sub n, n plus 1 times the reciprocal of u sub n, instead of dividing by u sub n. Because you're going to end up doing that anyhow. All right, so here's u sub n. And here's u sub n plus 1. Yeah. How about that? Thank you. Getting a little crazy here. Okay. We're multiplying with the reciprocal, right? Of u sub n. We said that. Do as I say, not as I do. Okay. Okay, and this is the u sub n plus 1. By the way, n plus 1 is n plus 2. Okay, and let's do something here. What's 2 times n plus 1? 2n plus 2. So I'm just going to write 2n plus 2 all factorial. Okay. Oh, good boy. Does anything reduce? Let's put it that way. Usually that's what happens. N plus 1 factorial and n plus 1 factorial. Yeah, I know. I'm going to stop right after this one. Yeah, thanks. I know, I was thinking that, but it's okay. All right. N plus 1 factorial to n plus 1 factorial does what? Goes away. Good. N factorial to n plus 2 factorial. What does that become? Like 5 factorial over 7 factorial. That'll be 5, 4, 3, 2, 1. 7, 6, 5, 4, 3, 2, 1. The 5, 4, 3, 2, 1 cancels and the 7 times the 6 remain. So what's left? I get left n plus 2 times n plus 1 on the bottom. N factorial into n plus 2 factorial is n plus 2 times n plus 1, no factorial. All right, so this into this reduces to that. This cancels that. What about this guy? 2n factorial to 2n plus 2 factorial. Like if n is 10, 20 factorial into 22 factorial. Leaves 22 times 21, right? Isn't that 2n plus 2 times 2n plus 1? That's it. So what's that limit? Now remember, we talked about this briefly way back in limits, right? The first day. If you take a limit of a rational expression like this, if it's top heavy, like you have n squared over n It goes to infinity. If it's bottom heavy, like you have n over n squared, it goes to 0. But if it's equal degree, if you FOIL this out, isn't this n squared stuff and this is n squared stuff? If it's equal degree, you look at the leading coefficients only. You ever hear of L'Hopital's rule? That's L'Hopital's rule. If you take the derivative of the top, seventh of the bottom, enough times such that that limit exists, you're going to get, what is the leading coefficient if we FOIL this out? 2n times 2n is what? 4n squared. What is it on the bottom? N squared. What's 4n squared over n squared? 4. So you get a limit of 4. We never did L'Hopital's rule, but have you heard of it? It would probably be easier if you FOIL this out. Does it reduce though? I can't reduce it more than that. N plus 1 is not a factor of well, actually, I'm sorry. I could do something here, but I can't do something there. Yeah, you can reduce it more, but you're still going to end up with some L'Hopital stuff going on, okay? Anyway, the point is that rho is 4. What does the ratio test say about rho is 4? Rho is supposed to be, for convergence, rho is supposed to be what? Less than 1. Is it? No. Therefore, divergent by ratio test, because rho is greater than 1. It's 4. So whatever it adds up to, it blows up. Okay, and this is where I'm going to stop. Okay, so we covered all the tests you need to know.